this week. Today we have a talk by Chungang Chen about the development of high-order adaptive global models by multi-moment constrained finite volume schemes.
Last Friday, Professor Xiao has already gave a seminar on high-order schemes by using multi-moment or multi-moment finite multi-moment or multi-moment constrained finite volume schemes. So today I'm going to introduce the application of these schemes in atmospherical flows. The title of my talk I just said the development of high-order adaptive globe models by multi-moment constrained finite volume schemes. The co-authors, Professor Xiao from Tokyo and Dr. Li from Chinese Meteorological Administration, and also Dr. Yi from Osaka University, Japan. Okay, here's the outline of today's talk. It's now clear, including 1, 2, 3, 4, 5 parts. First, the background of our study, and second, globe shallow water models on structure grid. And the third is globe shallow water models on unstructured grid, and also a two-dimensional non-hydrostatic model, and also a very short summary. First, I would like to introduce the background of our study. So the first point of view in our study is the computational meshes with quasi-uniform grid spacing is preferred in our study. So there are several such kinds of grids developed recently. So I guess every people in this room must be very familiar with these grids. So in our study, we classified this grid into two types. The first type is multi-domain structured grids. So the representative ones are cubic sphere grid and yin-yang grid. So on cubic sphere grid, so we have 6 identical patches to cover the whole globe. Within each patch, the local collinear coordinates can be constructed by a mnemonic projection. So it is easy to use the numerical schemes developed on the Cartesian coordinates. If the ghost cells is provided along the boundaries. But the major disadvantage of using cubic sphere grid for high-order models is here, the boundary. If the mnemonic projection is used, we can find the discontinuous coordinates along this boundary, and we always observe the large numerical errors around this area. So the right panel is yin-yang grid. Yin-yang grid consists of 2 components. Each component is a part of the traditional latitude and longitude grid. So it is very attractive because we can easily move the existing codes to this new grid with a quasi-uniform grid spacing. But there are also problems, the overlapping areas. So these overlapping areas make it very difficult to globally conserve the total mass. So it's first type. The second type is unstructured grid. So in spherical geometry, we usually use icosahedron grid. First, we project planar icosahedron onto the sphere surface, and then we can use 2 types of elements to cover the whole globe. So one is triangular element, and another is hexagonal element. So they have this grid have very uniform grid spacing, but they are unstructured in nature. So the numerical frameworks should be very different from what we have used for latitude and longitude coordinates. Some new techniques should be used for developing the high performance globe models on this unstructured grades. So that's for the global computational grades in our study. The second point of view, so we use a high order scale with local reconstruction to build the numerical models in spherical geometry. Here is a list of reasons why we use such kind of schemes, but this list must be incomplete. So first, the flows in atmospherical simulations are usually very smooth, but with very complicated structures. So it's very different from the high-speed aerodynamics, where the research focus on the shocks and discontinuities. So there are two ways to improve the numerical results. One is to increase the convergence rate or accuracy order, and another is to refine the computational grades. So for such smooth but with complex structures, the P refinement, that is to increase accuracy order, is usually much better than H refinement. It means to refine the computational grade. The reason two, second reason, so use the local reconstruction usually are very helpful for efficient and accurate implementation of the information exchange over the different domains. We have just mentioned the patch boundaries between different patches on the cubic sphere and the overlapping areas on the yin-yang grid between two components. So often we often found the large error around that areas, and the local reconstruction is useful to reduce the errors generated there. The second reason is for unstructured grades. The local reconstruction usually use a very compact stencil, so it provides a very practical way to construct high-order schemes on unstructured grades, and it helps to develop numerical models on icosahedron grade with high efficiency and robustness. The last one, the local high-order numerical schemes often they are computationally intensive, and these schemes will come to use on the massive parallel computers because they can achieve the high scalability. Here is a reason why we use the local high-order numerical schemes. There are several kinds of numerical schemes with this property. I think the popular ones include DG scheme, spectral element scheme, spectral difference scheme, so and also the multi-moment finite volume schemes. So it has been introduced by Professor Xiao, so today I'm not going for the details. I just would like to introduce the numerical formulations for atmospherical flows and show you some numerical results of widely used benchmark tests. So that's for background. And the second part is globe shallow water models on structure grade. So structure grade include two. The first is cubic sphere, and another is yin-yang grade. So if we want to construct high-order numerical schemes in curvilinear coordinates, first thing we need to do is to rewrite the governing equation into the curvilinear coordinates. So here is the general form of shallow water equations. So it works on both cubic sphere grade and yin-yang grade, but with different metric tensor G, and the dependent variables or the predict variables here is water depth and u, v are components of covariant velocity, and other important quantities include square root of g, it's Jacobi of the transformation, and also tilde u, tilde v are components of contravariant velocity. Okay, here is the governing equation. It works on both grades. So next, if we want to develop a finite volume formulation, usually we rewrite the governing equation into a flux form. So here the predict variable is square root of g times h and u and v. So if we use a finite volume formulation to update the continuity equation, so this quantity will guarantee the global conservation of the map. Okay, here's the Jacobi matrix and its eigenvalues of the flux vector. These values will be used in flux splitting. So as we know, the multi-dimensional numerical framework on structure grid can be straightforwardly constructed based on the one-dimensional building block. So here we just briefly introduce the numerical formulations for one-dimensional case, considering this one-dimensional hyperbolic conservation law. So first, the first step, we need to define the degree of freedoms. Remember, we are going to develop a high-order numerical scheme with a local reconstruction, so more than one DOFs are defined within each control volume, like shown in these three figures. So 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5 degree of freedom are defined for within each control volume for third order scheme, fourth order scheme, and fifth order scheme. So the DOFs can be updated by using this formulation here. This capital F means spatial reconstruction for flux. So if we want to preserve the accuracy, this spatial reconstruction of flux should be one order higher than the reconstruction polynomial for unknowns. Here we choose P plus 1 constraints for constructing this flux reconstruction. There are two types of constraints. The first one is first order derivatives of flux and interface between different cells. There are two for each control volume. And the second type is P minus 1 point values of flux and constraint points. So with this P plus 1 constraint, we can get a piece order reconstruction polynomial for flux. Then we can update the degree of freedom. So here, the flux reconstruction polynomial is a Hermite type interpolation. So this is a key point to distinguish our multi-moment scheme from the other collocation methods. And the multi-moment concept gives us a large flexibility to design the numerical schemes with different numerical features. And this is just one option, and there are large space for the explorations. Okay, so now the last task is to.
So the flux is continuous, and its derivatives are continuous at element boundaries.
It depends on the location of
Okay.
of your constraint point and also solution point. If
Not
you
necessarily.
give the DOF here, so the flux, the point value is continuous. Okay, the left task is to determine the values of these constraints. So for point values of flux and constraint point, it is easy to be calculated by the values of unknown and this constraint point, because in general the constraint point is not same as constraint point is not same as the solution point. So the value of unknowns should be interpolated from this interpolation function. And the second one, the value of first order derivative flux and interfaces, usually determined by solving a derivative Riemann problem, like this formulation, the derivative flux and left interface of the cell CI. And here is the reconstruction polynomial for unknowns, and subscribe I minus 1 denotes the left cell, and I denotes the right cell, and A plus and A minus. So it's determined by the approximate Riemann solver you choose in your scheme. Okay, with these formulations, so we can accomplish the spatial discretization for the degree of freedom, and the time integration in our model is usually accomplished by using explicit longer quota schemes. This relation always holds in our numerical formulations if the coefficients omega g is determined by the reconstruction polynomial of unknowns. So it is very easily to be proved. So according to this relation, our numerical scheme is conservative if the flux and the interface between different cells is continuous. Okay, there's still another question. Is how to define, how to determine the location of the DOF and constraints. In fact, in Professor Xiao's presentation, he has given some numerical tests that it shows the location of DOF is not a sensitive matter in our numerical schemes, but the location of constraint indeed is influence the numerical property of multi-moment schemes. So here, spectral analysis of linear equation. Okay, S is the amplification matrix, and this figure gives all eigenvalues of this matrix S. We use two schemes with a different location of constraints. First one is the CMMC5, so the constraint located at the Gauss-Lobato points. And second one is CMMC52, the constraints are equidistantly defined. So if we track this figure, this green rectangle denotes the eigenvalues of CMMC52. It means equidistantly defined. The eigenvalues is more close to this imaginary axis. So it means maybe CMMC52 scheme has a better numerical property. For example, the larger CFL number, the smaller amplitude error and the smaller phase speed error. But we also observed here very small, but in fact it's a positive value. So it means the CMMC52 scheme is weakly, slightly unstable. So in present study, we use CMMC5. That is, we define the constraints and Gauss-Lobato points. But it was further investigation because it's slightly unstable. So if we choose some proper time integration scheme with some numerical diffusion, maybe it can stabilize the scheme CMMC52. But just in present study, we use CMMC5. Okay, now let's show you some results on qubit sphere. So first of all, we would like to show the convergence rate. The convergence test conducted for advection equations and also shallow water equations. The first one is advection case. The initial condition is a very smooth sine wave. So according to the numerical errors by models of different orders on refining grades, we can find all models have achieved its theoretical accuracy. The third, fourth, and fifth order convergence has been achieved as expected. This is for advection equation. The next one, the convergence test for shallow water equation. We use Williamson standard test case 2 because this test case has a very smooth distribution, and also we know the analytic solution and same as the initial condition. So the flow direction is northeast direction, corresponding to alpha equals pi over 4. It's most challenging case on the qubit sphere. Also, we test models of different order on refining grades. According to the normalized error, both error L1, L2, L infinite. So we found the theoretical accuracy has been achieved as expected. So the numerical, the multi-moment schemes are extended to curvilinear coordinates and then applied in spherical geometry without losing any theoretical accuracy. So in this slide, I would like to show you the numerical results of Rossby-Horowitz wave. So these results, maybe it's not so clear, but these results are calculated by the model of different orders. This one is by third order models, fourth order models, and fifth order models. But during the computation, we use the same number of DOF and the same time integration interval. So for different tests, the computational cost is almost the same. But you can see the result is very different. Obviously, the most accurate result is obtained by fifth order models. Difference is here and also here. So the fifth order model produced a very similar result compared with the spectral transform solution, even on this considerable cost grade. So it tells us the high order convergence rate or accuracy is of essential importance in atmospherical simulations. Okay, we have also tested many widely used benchmark tests, but there's no time to report each of them. Just another example for case 5, the flow over isolated mountain. So these results are calculated by fifth order model, and on this cost grade, the height field agree well with the spectral transform solution. So next, present model conserves the total mass, but not for the energy and entropy. So this is the energy and entropy errors for case 5, flow over the isolated mountain, and we calculate this test with different with model of different orders, but same as previous one, we keep the degree freedoms, number of degree freedoms, and the time integration interval and sim. So we can see to increase the accuracy order or higher order schemes can also reduce the conservation errors for total energy and potential entropy. So the higher order models is very useful in atmosphere simulations. So this slide shows some results from first order model on yin-yang grid, because yin-yang grid is a structured one, so our results look very similar to what we have described obtained on the cubic sphere grid. So I will not repeat to report each of them, but one more thing, like here, the overlapping areas indeed influence the numerical accuracy, and also we made a substantial difficulty to develop a numerical scheme with global conservation on the yin-yang grid. Okay, that's all for structure grid. And we also developed a global AMR model with the application of the cubic sphere grid. So since each patch of cubic grid is a structured grid, so it is easy to implement the AMR technique developed for any on Cartesian grid. So all we should do is to design how to exchange the information between different patches. Maybe the code is a little complicated, but the basic idea is very simple. So I just want to show you some results. First, the advection result for the cosine Bayer advection. So for this test, except this area, the transport field is 0. So if we just refine this area, the errors should be reduced, same as we refine the global computational grids. Here the errors and CPU times on different grids. We can see the result is reasonable. For example, this number means the level of a grid. If this number is 1, it means a uniform grid, and 2 is a 2-level AMR grid, and 3 is 3-level AMR grid. We can say the finite resolution. If finite resolution is same, the errors are very close to each other. Okay, and also by using the AMR grid, the CPU time has been obviously reduced. The results in the AMR techniques works well in our multi-moment model. There another advection test with a very complicated structures. It's in fact it's a non-smooth deformational flow. Okay, even for these complex structures, so our AMR model can accurately find the area with large gradients.
Are the grids dynamically refined?
Yes. Tracking the change of structure.
Could you say quickly how you do it? Well, you need a rule for adaptation, so.
This one?
No, could you explain quickly how you make a dynamic adaptation?
Dynamic. So
it's time dependent, right?
yes, time dependent.
So how do you do it?
According to the gradient. If gradient is larger than some threshold, the grade refine the grade. Okay, this case is for shallow water equations. It's a flow over isolated mountain, case 5. The result is calculated on a 4-level AMR grade. Here is a normalized error. It is calculated based on the difference between present numerical results and spectral transform solution on grid with very high resolution. So this line. The second line is numerical errors of results on this 4-level grid, and the lowest line is for numerical errors on the uniform grid with a resolution same as the finest resolution of this AMR grid. So the errors are the difference between errors are not is very small. So the same test has also been tested in this paper by using spectral element AMR model and also finite volume AMR model. So the spectral element method produces a similar result, but if we use a finite volume model, the normalized errors on the AMR grid may be much larger, maybe approach this point. So from this result, I believe the local reconstruction is also useful for improving the accuracy on AMR grid to reduce the errors due to the different resolutions on different levels. Okay, there are some results from adaptive model. So next, I would like to introduce the globe shallow water models on unstructured grid. So I use this planar hexagonal element to introduce our numerical formulations. Remember, we are going to development high order scheme with local reconstruction, so we define more than 1 degree of freedom within each control volume. So in this case, we define 7 DOFs. They are point values. 6 of them are located at the vertices of the element, and another one is located at the center of the element. We also define 2 kinds of constraints, or 2 kinds of moments. The first one is PV moment, point values. It is defined at the vertices. And the second type is volume integrated average. It is defined over the control volume. So a local quadratic spatial reconstruction can be obtained by using the information provided within just a single cell. So you can see a quadratic spatial reconstruction with 7 coefficients, and it is determined by solving this equation set and determined by 7 DOFs. Using this spatial reconstruction, so we can connect the constraints and the DOFs. So in this simple case, the DOFs located at vertices are equals to the PV moments, and the DOF and the center of the element is related with the constraint with this relation, and the coefficients can be obtained by integrating this spatial reconstruction over the hexagonal element. So if we have accomplished the spatial discretization for different moments, then we can update the DOF. Well, we consider this 2-dimensional hyperbolic conservation law to describe the numerical formulations for the schemes on unstructured grids. First, different moments are updated by different form of formulations. The PV moment is updated by this differential form equations. So we need to calculate the derivative of flux at this point. same as previous formulations. This derivative flux is calculated by using a derivative Riemann problem. Okay, the VA moment is updated by flux form formulation. So it is obtained by integrating this governing equation over the hexagonal element. So it guarantees the numerical conservation. So after integration, we obtain this formulation. So we need to calculate it here. The line integration of flux vector along the boundaries of element. So as we have mentioned before, we also test the numerical schemes on triangular element. So on triangular element, the DOF, the configuration of DOF is like this, except the vertex cell center. Also, the center of boundary edge is used to define the DOFs. Also, 1, 2, 3, 4, 7, 1, 2, 3, 4, 5, 6, 7. So 7 DOFs, and we can still use this spatial reconstruction. There are 7 coefficients. The configuration of DOFs on pentagonal element, which there are 12 pentagonal elements on icosahedron hexagonal grid. So it's a little different because there are only 5 vertices, and so we define 6 DOFs within each control volume. The quadratic spatial reconstruction is also a little different. 1, 2, 3, 4, 5, 6. 6 coefficients and determined by 6 DOFs. The formulations to update the DOFs are almost the same as we have just described for hexagonal grid, hexagonal element, so will not repeat. Okay, here is numerical results. First of all, we would like to test the convergence rate for both the diffraction equation and shallow water equation. The diffraction equation, we still use a smooth sine wave in spherical geometry. There are 2 tables. The top one is for triangular grid, and the bottom one is for hexagonal grid. You can see third order accuracy has been achieved as expected. And for shallow water equations, we still use the Williamson standard test case 2 on refining grid. It's a third order accuracy we have obtained. So again, we extend our numerical scheme to unstructured grids and extend it to develop the globe models and without losing the theoretical accuracy. On these 2 grids, we also test a lot of benchmark tests, but has no time to report each test here. So I just these 2 representative ones, the case 5 by case 5 and case 6. These 2 panels are case 5 by on different grids. This is for triangular and this is for hexagonal, and also case 6 on the triangular and 6 on the hexagonal grid. So the numerical solution agree with the spectral transform reference solution. And also the other benchmark tests, the numerical results of other benchmark tests, it looks good and reasonable. There are more results and comparisons with existing models in our papers. Okay, that's for the spatial discretization in horizontal direction. So if we want to develop a 3-dimensional dynamic call the next step, we need to check the performance of our numerical scheme in the discretization in vertical direction. So we have developed a two-dimensional non-hydrostatic model. So this work is done by Dr. Li. Maybe maybe someone has met him in this room in September. He came here for PD workshop and reported his work. Okay, the two-dimensional non-hydrostatic system is all a system with gravity. It is written in carrying coordinates to construct a high-order numerical scheme. So, because it is also a structure grid, so the numerical scheme we have developed on the qubit sphere can be used here directly. So another thing should be pointed out is here we widely use this thermodynamics variable splitting. We split the thermodynamic variables, rho, density, pressure, and the potential temperature into a reference state and deviation.
The obvious point is this is compressible.
Yes, compressible.
So it's more time consuming than taking anelastic approximation.
Sorry?
It's more expensive than anelastic approximation.
Yes.
Yeah, okay.
Okay, again, we rewrite governing equation into flux form. And here is the unknowns, the predictable variables, and also the Jacobian matrix and its eigenvalues will be used for flux splitting. So I will not repeat the formulations because it is almost the same with the formulation we used from the qubit sphere for the shallow water equations. Just show you some results. First one, the rising thermal bubbles. So this is for potential temperature perturbation and wind and velocity in horizontal direction and velocity in vertical direction. All these results are calculated by the first order model. So very symmetric structures are perfectly reproduced. So the results seems good and reasonable. Second one, the density current. Yeah, this one. It's not clear. The density current. All these results are calculated by first order model with different resolution. Even on this very coarse grid, we can find the structures and the front, the location of front is almost same as fine resolution. We also test the convergence rate by models of different orders and also on the refining grades. This picture shows the results by third order model. This picture shows the result by fourth order model. So obviously the first order, if we use higher accuracy order, the results converge more rapidly. So it tells us the higher order numerical models are also very important for the discretizations in vertical direction. Okay, the last one is the mounting test to check the performance of a numerical scheme to treat the bottom mounting. There are 5 bottom mountings, and we use these hybrid coordinates. Here is the result by the wind field. Wind field is a horizontal wind and vertical wind. It's obtained by models of first order accuracy, and the thick line is numerical results, and also the thin line is semi-analytic solution by using linear theory. Okay, we can see it agree well with the numerical results agree well with the semi-analytic solutions, and also this result is competitive to other methods like DG or spectral element method. Okay,
What's the resolution for that one?
resolution. I'm sorry, I cannot remember exactly. Or maybe I
I
can.
think it's approximately the same as Frank used in his paper, PhD paper 2008.
I don't know that one either.
Yeah, approximately the same.
Maybe this is on course grade. But, I cannot remember exactly because this work is done by Dr. Lee. Okay, the conclusion. So we have already developed a promising numerical framework for global models using multi-moment schemes. So these models are accurate. The global models achieve the theoretical accuracy of multi-moment scheme for all types of spherical coordinates, including structured ones and unstructured ones. So second, the global models using the multi-moment scheme is easy to be implemented on different types of spherical grids. We do not use much extra manipulations, and these models are robust. Multi-moment formulation obtain good results on the different grids that have a substantial different structures. Maybe this sentence is not correct. Okay, the outlook for future work, and there is an ongoing project. We are developing a three-dimensional dynamic core in collaboration with Chinese Meteorological Administration and supported by Ministry of Science and Technology of China. So I think it's potential candidate dynamic core used for next generation numerical weather prediction model in China. That's all my talk. Thank you.
Other questions?
Very nice. I have a comment and then a question. The first, a comment. So the icosahedral grid can be indexed directly.
Yeah.
So the icosahedral grid is not an unstructured grid. Now there are variants that are, but I don't think that's a very good example for you for an unstructured grid, because you can address you have 10 panels and you can address them by I and J, just like you can a regular Cartesian mesh.
Yes, we treat it as unstructured ones.
Okay, yeah, that's fair. The question. So in one of your pictures, you showed point-wise and volume integrated values on, say, a triangle.
Yes.
And I think you had 6 around the boundary and then 1 in the center.
Yes. Oh, yeah.
There we go. So now, so P1L, there are going to be about 5 other of those, right? Because there's going to be 5 other triangles.
Yes.
And so you're going to have 6 values at that vertex?
No, the same values.
Same value.
These values shared by different triangles.
Okay. Now, but the reconstruction is local.
Yes.
So how do those different values become the same? So if the reconstruction for the vertex is local to that triangle.
Yeah. So in fact, this DOF defined here is updated by a derivative Riemann problem, like this, or like here. So if we use the same value of derivative of flux, so the value will always keep same. And this derivative of flux is updated. It's obtained by using derivative Riemann problem. So we can always keep the values of that DOF same during the computation.
Okay, so there really aren't 6 of those vertex values. There's really just 1, and they're shared across all the triangles that own that vertex.
Yeah.
Okay.
Yes.
Thank you.
Further questions?
Yeah, I have several questions, so probably you can't answer all of them. You did the Fourier analysis of the transport equation with the eigenvalues. Right?
Yes, it's for transport
For
equation.
transport. And did you do the same for shallow water, for instance?
Not now.
But if you
Maybe it
interesting to
was,
see if you have, I don't know, spurious branches
Yes,
or
yes, yes. We're going to do this.
And in terms of allowed time step, do you have constraints as the order is growing, or either your CFL number it's always close to 1, or it's smaller than?
So the CFL number is smaller than 1. And, yes. So the CFL number, yes, it's smaller compared with the traditional finite volume scale. Because if such kind of schemes with local reconstruction, they always has a very restrictive CFL number. And sorry, maybe I missed it.
Yeah, well, the background was, for instance, in DG you have a severe restriction
Yes.
of the time step when you go to higher order. So
Yes,
is it the same with your method, or?
yeah, it's same, but maybe our method, the maximum available CFL number is larger than DG, but its CFL number becomes smaller when we increase the accuracy order.
Okay.
Are there further questions? That seems not to be the case, so let's thank Chungang again.